So, as you all probably heard that the last solar minimum was longer than expected and deeper than expected. And I'm going to try to give you a brief overview about the nature of the solar activity and what are the physical processes that cause the solar activity. And I will try to show in general how much we understand or don't understand the sun yet and the way it works. So I will start with a brief historical overview about the solar cycle and sunspot observations. And then I'll describe the solar magnetic field and the solar convection inside the sun. That's the driver for solar activity. Then I'm going to talk about the models for the solar cycle and models that we have to try to understand the solar cycle. And I'll talk about it more deeply about the last solar minimum, which is a great problem. And I'll conclude with what we still understand or don't understand. So as you saw this slide before, the solar cycle was first discovered in the early 1700s, even though there were some sporadic measurements before that. And you can see that the solar cycle clearly appears as a time series here. And it was discovered by Samuel Schwab. He worked in the observatory in Germany in 1843. He is the first one to note that there's a cyclic activity in the sunspot data. And then Rudolf Wolf, who also worked in that observatory, he reconstructed back the data up to 1745 and even to earlier times. And solar astronomers have found that it's useful to define a standard sunspot number index to quantify the level of activity of the sun. And they also noted that there was a period of time where the number of sunspots was really low. That's the famous Maunder minimum. And later it was discovered that it has some atmospheric implication of a mini ice age. The Earth was really cold during that time. And the Maunder minimum was actually first discovered by Sporer, who later on worked with Carrington on, and they reconstruct the famous butterfly diagram. What we did, they measured the number of sunspots on the solar disk, and they took slices of longitudinal average. So they averaged the number of sunspots over a circle at certain height or latitude on the solar disk, and they averaged that, and they just stacked these strips with time, and they note that the sunspot migrate from the beginning of the cycle. They appear at around 30 degrees from the equator, and then as the cycle progressed, they noted that the sunspots migrate towards a lower latitude, and then at the beginning of the next cycle, they jump back to higher latitudes and so forth and so on. You can see that there are some cycles that the spots appear at higher latitudes, while in some others they don't. And the magnetic nature of the cycle was discovered by George Hale in the early 1900s, and he did it using so let me just I'll describe Hale with some background. He studied at MIT, and he worked at Harvard, and later in Berlin. He was a professor at University of Chicago, and editor of the FJ in Astronomy and Astrophysics. He hired Shipley and Hubble. Each of them later had a major discovery in cosmology. So he was the guy that actually was responsible to hire them. And he works in many observatories. He developed solar observatories. He was the first one to do that. And he was schizophrenic, and apparently he thought that he had this visitor from an elf that told him what to do or something like that. This is all, by the way, from Wikipedia. It made my life much easier to make this overview. And so you can get a lot of information with Wikipedia and the internet now. So it's pretty amazing. So what he did, he developed an instrument that he can measure Zeeman splitting over the solar disk. And Zeeman splitting is a measurement of magnetic fields. So he was the first to do that, and he discovered that the active regions or the sunspots are regions of very strong magnetic fields. And he followed the development of these sunspots in terms of the magnetic activity, and he discovered what we now call Hayes' law. And it states that the magnetic polarity of sunspot pairs first appear in the same polarity in each hemisphere. You can see, for example, here in the northern hemisphere, we have the positive polarity closer to the pole and the negative polarity closer to the equator. And in the other hemisphere, it will be the opposite. This is one thing he discovered. And again, they opposite across the equator. And also he discovered that when the field reverses, when we get to the next cycle, this polarity reverses. So we move from positive and negative to negative and positive, and the opposite behavior in the other hemisphere. And this essentially tells us that the magnetic activity and the sunspots are related to the behavior of the magnetic field of the sun. Now, and Hale stated that the cycle is of 22 years, but we still continue to use the 11 years for the solar cycle, mostly because of historical reasons. But the actual cycle is 22 years. We start with certain polarity, and then the field reverses after 11 years, and it gets back to the original polarity after 22 years. Later on, Harold Babcock and his son Horace, they actually measured the magnetic field of the sun outside of active regions, like you see here. This is the real data butterfly diagram from 1975 to present day based on the modern solar observatories. And they discovered that the sun is magnetized even outside of active regions. And not only that the spots field reverses every 11 years, but you can see also that the polar field, which is represented by positive polarity in yellow and negative polarity in blue, you can see that we start with yellow and blue, and then after 11 years, the field reverses to blue and yellow. And they stated that there is a low level or a low order dipolar field of the sun that is also reverses every 11 years. So it's not only the spot, but it's also a weak dipole background field in the sun. And today we know in general that here you can see at the top, this is X-ray images from Yoko. And we start with solar maximum here on the left, and we approach solar minimum here on the right. And you can see that the level of, or the X-ray luminosity reduces. You can see here we have a lot of bright regions, which is an indication of high X-ray activity. While here the disk is essentially dark during solar minimum, a very low X-ray level, X-ray activity. And the X-ray activity is a measure of the active regions in a way. So you can see that there's a change between solar maximum and solar minimum. And if we look at these white light images, essentially the sun is in the middle, and the sun is blocked by this occultation disk, so we can see the solar corona. You can see the structure of the solar corona magnetic field during solar maximum here, for example, where it's really complex. It doesn't really have any particular shape. And during solar minimum, like here, you can see it has a dipole shape, which represent the dipolar field of the sun during solar minimum. Oops. Okay. So now I'm going to talk about the nature of the solar cycle. And the nature of the solar cycle starts with convection or motions in the sun that moves the magnetic field, converts the kinetic energy into magnetic energy, and changes the magnetic topology via the motions in the sun. This is a schematic of the sun. Here is the core where the nuclear reaction takes place. And we need to transfer this energy out from the sun. So we do it via radiation in the radiation zone until we get to a point where the temperature changes. The temperature gradient is the change of temperature from the top of the radiation zone to the surface is so steep that we must have convection to take place and transfer this heat from here to here. So we start to build up convection cells that it's essentially a circulation. It's like a boiling water in a pot. And you have this convection cell that is simply a circulation of the plasma, which is ionized gas here in the convection zone. And you can see that, in the schematic we see sunspot here, which are regions of very strong magnetic fields. Now, when we talk about the dynamo, I need to explain what is the frozen-in concept. In plasma, the conductivity is so high that any motion of the particles, the ionized particles, causes the magnetic field to adapt really quickly to the motions that they do. So it seems like as the fluid is moving, the field is glued to it, like that. So the fluid drags the magnetic field with it and changes it. So this is the frozen-in concept. It's an MHD concept, magnetohydrodynamics concept. And essentially what we mean by that is that magnetic fields are dragged by the convecting motions of the plasma, and that the solar cycle in general is related to the circulation of the magnetic field via the convection motions of the plasma and the transfer of kinetic energy to magnetic energy from the plasma to the magnetic field. We have amplification of fields, we have compression of fields that makes them stronger in certain places, and we also have the change of the magnetic field via these motions. And what are the main motions we have in the sun? In the solar interior, again, I'm talking about the convection zone, which is the top 1/3 or so, or 1/4 of the sun, solar radii. So the main motion we have is differential rotation, is this azimuthal motion, and it's related to the solar rotation. But the sun, we know now, based on helioseismology measurements, that the sun has differential rotation, which means that in the equator, the rotation is faster than in the pole, with about 20%. So the equator rotation is about 20% faster than the pole. And this change is one of the main effects when we talked about the generation and evolution of the solar magnetic field. In addition, we have meridional circulation, means that we take stuff from the equator towards the pole, we take it deeper into the bottom of the convection zone, and then we take it back to the top. So it's a motion from the top to the bottom and from the equator towards the pole. And this motion is much weaker than the differential rotation. The solar rotation at the equator, at the surface, is of the order of 2 kilometers per second. And these motions are about 10 to 20 meters per second. So it's about an order of magnitude lower. Almost 2 orders of magnitude. And this schematic, it's a meridional cut from the sun. This is the radii, and this is the azimuthal, the angle. And you can see that we have gradients in the rotation, not only from the equator to the pole, but also we have some across the convection zone. We have some gradient in the rotation. The radiation zone seems to rotate solidly, so it has only one rotation, while in the convection zone we have this differential rotation that is dominating the motions. In addition, we have start playing. Yeah. So this is a very nice movie from the Swedish Royal Solar Telescope. And it's an active region. You can see that it's dark here because the magnetic field pushes the plasma. So this area is colder, and this is why it appears darker. But you can see that there's stuff bubbling all around it, a small-scale stuff. And these are the small convection cells that rising due to the convection. And it's really like a boiling water. And this stuff is hot, and it rises in the middle, and then it cools down here, and it falls to the side. And these are the regions of this kind of lanes, as you can see it. So this is a small-scale motion that also contributes to the modification of the magnetic field, in contrast to the solar differential rotation, which is a large-scale motion. And because the magnetic field is buoyant, we have this rising of what we call flux tubes. So imagine you have a magnetic field line like that at the bottom of the convection zone. Instabilities in the plasma cause this flux tube to rise, and it rises faster in the middle than in the side. So we have this generation of bent flux tubes as they rise to the surface. And here, these points in the flux tube at the surface, these are essentially the sunspot that we see. These are regions of strong magnetic field. They're colder, and this is how we see it in the surface from the top. So it's all related to magnetic field. Now, what is a solar dynamo? What is dynamo in general? If we put a magnetic field in a vacuum, it will decay after a while. So the question we would like to ask is how the magnetic field maintains itself. And we can look at that in terms of polodial field, which is a magnetic field that is essentially like that, vertical. It's a combination of the r and theta components. And an azimuthal, or what we call toroidal field, which is 90 degrees perpendicular to that. And we can ask ourselves, okay, let's say we start with such a magnetic field. Can we generate from that a magnetic field with this topology, and then generate from this one this topology back again? And if we can show that we can do it, we can say that the magnetic field moves from one topology to another and it maintains itself. So suppose we start with a polodial field, again meridional field. If we have differential rotation and it's faster in the equator than in the pole, you can see that here the field lines will be bent more than in the pole, and eventually we move from topology of polodial field to toroidal and azimuthal field. So we move from this to this, right? So differential rotation can generate the transfer from polodial to toroidal field. And then how we switch back from toroidal field to polodial field, we have these flux tubes that they rise to the surface, and because the sun is rotating, we have the Coriolis force that twists them back like that. So they will rise from toroidal field, and then we have the Coriolis fields twist them, so we can get back this polodial topology. And the combination of the rising of magnetic field with this twist, this tells us that we can get from azimuthal or toroidal field back to polodial field. And this movie essentially shows that. Oops. Get back. You can see that we start with polodial field lines. Then we'll have the differential rotation, stretch the field lines, we get the toroidal field. And then we have here this twisting of flux tube. You can see that we get back to polodial topology. So this was the conventional idea about the solar cycle based on a paper by Babcock in '61. But it was very conceptual paper. It didn't have a deep mathematical background. It was based essentially on observations. So in the past, since the 1980s or so, late 1970s, we had a more sophisticated models to simulate the solar dynamo and try to reproduce this quantitative phenomena in a more qualitative thing. And I'm going to show equations. Don't be scared. I'm going to talk about them really briefly and in general. So the induction equation essentially tells us about the evolution of the magnetic field in time. This is this term. It's the change of the magnetic field with time. So, oops. So this term. And then the field is changing by two things. One, the convections that I just showed you. The motions of the sun drag the magnetic field and change it. And mathematically, we describe it using this term. And then we also have field diffusion that can change the field. So the field, because of the conductivity is not perfectly infinite, we can have this diffusion of magnetic field lines that will change its topology as well. But in the sun, this term is very small in general. And it's related to so this term is related to the large-scale motions in the sun, the differential rotation, the stuff that happens on the large scale. And this term is more about the turbulent motion and the small-scale motions of the sun and how they change the magnetic field. Don't get scared again. So here, this is just, we can write this equation in terms of the polodial component and the toroidal component that I just showed you. And the only thing I would like to mention is this term here. And you can see we have BP, which means this is a polodial field. And we have this U phi here, which is the azimuthal motion. And this term is essentially describes the change of the field due to the differential motion, just like in the movie I showed you before. But if we write the component for the polodial field, so this equation tells us that we can get a azimuthal or toroidal field from a polodial component. But if we do the other way around, and this equation is described in terms of the vector potential, not at B, but it's essentially the same. If we have a polodial component, you can see that there is no phi component anywhere here. And that was a problem during the 1950s and before. that there was no way to get a toroidal field from a toroidal field. And then Parker in 1955, Gene Parker is a smart guy, discovered the solar wind, and he did a lot of interesting things. He was the one that suggested this Coriolis force twisting of the flux tubes, so we can get a poloidal field from a toroidal field. And mathematically it's described using this term, and you can see there's this alpha here, which is essentially just a parameter, that from that we can get a poloidal field from a toroidal field. And I'll get back to this alpha in a second when I talk about the component or the ingredients we have in any dynamo models that we want to do. So a dynamo model, essentially we need to take these equations, plug them into the computer, and solve them, and get some evolution of the field that we hope that will match to what we see. That's the modeling in general, right? So any ingredients that we need to have in a model for the solar dyno, one is the velocity. Of course, this is what the different motions that I described. We have this eta, which again describes the small-scale motion. It can be related to random convection motions, small-scale convection motions, or diffusion due to the magnetic reconnection, which I won't talk at all here, or some kind of turbulent motion in the plasma. And there are several dynamo models that this ingredient of turbulent gas or flow is the main driver for the dynamo. The other thing we have is this alpha, which is a parameter that controls how much poloidal field we get back from the toroidal field. And it can describe in different physical ways, but essentially at the end of the day it's just a parameter. And this alpha also is related to magnetic helicity, and I found the need to mention that briefly. What's magnetic helicity? You can imagine a magnetic field like a rubber band or a slinky, for example. And if we twist it, we store energy in it. So helicity is related to the amount of energy that we have in the twisted magnetic field. And if we release this magnetic field and we store some energy, it will break up and stuff will happen. So you can think about this airplane thing. Oops, stop working. That's fine. You can see the airplane, we twist the rubber band, we twist it, and then we leave it, and we get some energy that allows the airplane to fly. So the same thing happened with magnetic fields, and you can see here, this is an example from a simulation of a coronal mass ejection that Leon will talk about in much more details. You can see that it's highly twisted, and then if we take scissors or magnetic reconnection and we cut it, the whole thing will blow away because it has stored energy in it. So magnetic helicity is related to the storage of energy in magnetic field, and that can have some contribution to the evolution of the field for the dynamo action. So in general, there are several types of dynamo models. They can be 2D, like a meridional cut across the sun. They can have some of them are for solving the equation only for the surface of the sun. Some of them are 3D. And usually they look like that. You have some kind of solution for the magnetic field inside the convection zone. And what they try to do is to reproduce the butterfly diagram and some other observable things that we see. The most sophisticated models for the dynamo are more complete MHD models, which are magnetohydrodynamics. They solve not only for the evolution of the magnetic field, but for the coupled evolution between the motions, the density, the pressure, and the magnetic field. And because of that, they're much more sophisticated, they're much more complex, and they're much more expensive computationally. But you can see this is from a simulation by Ben Brown, and you can see that they solve for the magnetic field in 3D. And what they try to do is to reproduce cycles and reversals of the field. And here you can see the field changes from blue to red and back to red and from blue. And this is nice, but the problem is that they're so expensive that they cannot run it for more than one cycle yet. Of course, we hope that we'll have better computers soon and we can do better simulations. They can also have a relatively low resolution because they're so expensive computationally. So they're very limited to capture the small scale phenomena that I just mentioned before. So I can tell you that, for example, here they can get cycles, but they cannot really say why. So they kind of get what they want, but they cannot really understand the basic physics from these models yet. And this is a quote from the person, from Brent Brown. So I'm not making it up. So dynamo models are pretty successful in reproducing some of the observed features of the cycle. Helio seismology measurements become much better, so we have real data about the motions that we need to put in the models in order to obtain the solution. And models for the surface are extremely successful because they reproduce what we see. On the other hand, they're only 2D and they're limited to the surface. Some problems with these models, many of them are highly parameterized. So they have a lot of free parameters and we can just play with the parameters and get what we want essentially without a strong physical basis for doing that. Or saying why this particular set of parameters is the right one or is the one that we get what we want. The meridional flow at the bottom of the convection zone is unknown, so they need to make some assumptions about that. There's almost no feedback between the magnetic field and the motions except for these MHD models. And there's an over or underestimation of the polodial field because we have this alpha parameter and that we just control it. And again, we're not sure why exactly this particular value will give us what we want. And the small scale phenomena of the diffusion part is weakly captured in these models. And nevertheless, they're still very expensive. So they're not perfect at all. And there was a campaign in 2008, I believe, or maybe before that, to provide predictions for the next solar cycle, for cycle 24, based on dynamo models, based on some data analysis, anything you can come up. NASA asked for people to provide predictions for the solar cycle. And what's the problem? You can see that it covers all the range. So people say it can be really weak, it can be really strong. Nobody really knows, and now we start to get a new cycle, and it seems like the answer is somehow in the middle. So in my mind, this plot essentially represents the most how much we don't understand yet the nature of the solar cycle, because it can be anything. So I'm going to talk a little bit about the last deep solar minimum. It was longer than the usual one, and it has some features that I will describe in a second. And this is a nice quote I found in the NASA website. The sunspot cycle is behaving like a little like the stock market. Just when you think it hit bottom low, it goes even lower. So that was the situation. And you can see the sun actually went to bed. It was really long. This is from 2005. This is the solar disk. It's a magnetogram. It's a measurement of the magnetic field on the solar disk. You can see that there's essentially almost no sunspot. It's empty. And this is from last week. You can see that we have new cycle. An interesting thing that I just noticed that we have two strong active regions in the south and much more in the north. Did you know that? Okay. This is interesting. So I'll just briefly, I mentioned that some people mentioned that it seems like the cycle starts in one hemisphere, but it's still starting in the other one. So there's an asymmetry in terms of the cycle. So some feature of about the deep solar minimum. The polar coronal holes appear to be smaller. The polar coronal holes are the regions of the open field lines. It's a representation of where the magnetic fields are open into the solar system. And during solar minimum, we have these big coronal holes in the polar area, while during solar maximum, they can appear everywhere, essentially. So there was a weaker so the polar magnetic flux seems to be weaker during this last minimum. There's a 50 years low in the solar wind dynamic pressure, so the solar wind seems to be weaker. Very low coronal mass ejection rate, because we have no sunspot, and that's where CMEs come from. We have lost measured the heliospheric magnetic flux, so the magnetic field in the solar system near the Earth is the weakest ever measured. We have a 20 years low of solar radiance, which is the ambient flux that comes from the sun. We have a 50 years low of, in solar radio emissions. And there were, during 2009, more than 50 days, 50% of the days during the year were with no sunspots at all. So it's really deep solar minimum. Here I'll briefly show some analysis of some of the measurements we have. At the top, these are the, based on the EIT images or EUV images that we have from Stereo and Soho. And they did something like the butterfly diagram. They essentially average over the longitude and they stack everything together with time. You can see that in the previous cycles we had this polar thing at the top, seems as polar feature, which is absent in the last minute. And this plot here shows the torsional oscillations. And this is essentially the subtraction of the rotation of the sun with latitude from the average rotation measurements. So these are the residuals of the solar rotation. And you can see that in the previous cycle, we have this migration where they call it the equatorward branch and also the polar branch. So some stuff moves towards the pole and something moves towards the equator. And in the last solar minimum, you can see it's different than the previous one. So these are kind of indications about the deep minimum we're in it right now. This is an interesting thing, a paper. This work essentially states that CMEs takes helicity or remove helicity from the sun, and there are some dynamo models that claim that in order to maintain the dynamo, you must remove this helicity from the solar magnetic field, because this is stored energy. To remind you, you need to remove this stored energy so the field can kind of be relaxed and doesn't have energy within it. And one way to do it is via CMEs. You release the CMEs, they are twisted, and then it's kind of relaxed as the CMEs propagate into space, and this is a way to remove this energy. And this is a study of the polarity of the helicity in CMEs in the solar system. And you can see that there's a clear pattern in previous cycles, while in the last cycle there's obvious preference towards northern polarity. And you can see that the behavior is somehow different also when you look at CMEs in the solar system. So there are some pros and cons in having this kind of minimum. The pros is a small amount of space weather hazards occur, right? The satellites are fine, we shouldn't worry about them. It's an opportunity to study the solar wind and the sun in its kind of ground state. So CME is kind of messing stuff around. If we're interested in study the ground state of the sun, the basic level of the sun and the solar wind, this is a very good opportunity for us to do that. This unusual state of the sun brings solar physicists from different communities to talk with each other. There's a community of the solar interior, and there's a community of the solar corona, and there's a community of the heliosphere, and they don't talk too much with each other too much until the last cycle, and that was a good opportunity to bring these people together and start to talk with each other. And we got some really nice ideas about what's going on from this interaction. The cons in this minimum is that if you're interested in CMEs, it's a really bad period for you because there are not much CMEs to study. And Stereo was launched right at the beginning of this period, and essentially for 2 or 3 years they didn't have anything to look at. It's a bad period to study space weather. If you're interested in space weather, that's a bad period to study that. And it questions many theories and models about the solar cycle, because we thought we understand how it works, and then we had this deep solar minimum and messed things around. So, but this is actually a good thing because we have interesting thing to learn and ask about. So I'll conclude my talk. The recent deep solar minimum challenged many theories, just like I said, but it's an opportunity to study many new things. And dynamo models in general are partially successful, but they still have many problems. And in my mind, okay, I'll get to my mind in the next slide. They still have many problems, even though some of them reproduce the solar cycle pretty well. We cannot claim yet that we fully understand the solar cycle. because we don't have yet a really reliable tool to do that. We can make some predictions, but there's no way we can say, okay, this tool is better than the other, just like I showed in this slide, with many, many predictions that they cover all the range of possibilities. And of course, with the advancements of computational power, these models will be able to be run with much higher resolution and with more complete physics, so we will need to make less assumptions, and then probably the results will be more precise. So these models highly depend on the computational power we have. And now some personal view. On the theoretical level, we need to look at the solar heliospheric magnetic connection. So I am a great believer of looking at the sun as a single system from the bottom of the convection zone all the way to the heliosphere. And this kind of coupled study is almost not done at all. And I think we need to do it much more. And I'm promoting this kind of investigations among the communities. And we also need to look at other stars. And this is another thing that is rarely done because other stars have activity too. And this is just a measurement of one example of a star that we can measure magnetic fields in these stars, and we can follow their activity. And we have a large amount of data from astrophysics about activity and cycles of other stars. And I think if we look at that, combining with the solar data we have, we can learn much more about our own sun. And this is essentially summarizes what I said. We need to combine solar physics where we have the details with astrophysics, that we have different statistics of cycles and activity. And I'm sure we can learn a lot by doing that. And this pessimistic statement refer only to the solar cycle. And we still have pretty good tools to predict space weather. And Leon will talk much more about that. So I think in terms of space weather, we can do much more than what we can do with the solar cycle itself. Thank you.